Hello, everybody. Today we're going to do a lesson on solar radiation. Really, in the last half of our semester here, all of quarter two really has a lot to do with solar radiation and it driving a lot of the processes that we're going to be talking about for the duration of our time together this semester. So, what we're really focused on here is 1-1, talking about energy and how it moves, energy from the sun specifically, how it radiates to different bodies. Particularly, we're talking about Earth. Um, Analyzing data to make claims that one change to Earth's surface can create feedback. So again, we're going to be talking about that balance of energy and how that can really affect everything else. 2-4 describing how causes of short-term, long-term variations in the flow of that energy specific to solar radiation can change systems on Earth, can change systems within weather, and then weather, of course, over a long period of time is climate. Sorry, I had to pause right there for just a second. All right, so we're going to talk about energy a lot, and you're going to be like, "Wow, does this really fit in?" The transfer of energy and having a good foundation in what energy is and how it moves is so relative. It is so foundational to understanding solar radiation and how it drives processes here on Earth. So we are going to begin with that in mind. Energy. What is energy? How is it transferred? Energy, heat, and temperature are related. We're talking about weather, we're talking about oceans. Those are the driving concepts. Energy, heat, and temperature are related. Okay, so here's an example. As you heat water, you transfer electrical energies that coming from the eye of a stove there. It becomes thermal energy. It's transferred then through the water to the water molecules. And then that water is actually moving via convection. Convection, we've talked about so much. We got a lab coming up on that. So, convection, we talked about interior Earth, how the heat differential causes heating, rising, cooling, falling of material. And also, we're going to talk about convection within the oceans. That's driving ocean currents on small scales and global scales. And then we also talk about convection in the atmosphere and the water cycle and what that does in our atmosphere for our weather. So, very, very key concept here is energy and also using that term there, convection. Why are we talking about this? It's the temperature difference. So you're gonna get so tired of me and your teachers saying that a heat differential, temperature differential. Again, you're gonna probably know that concept in your sleep by the end of this quarter. All right, the law of conservation of energy. Energy is neither created nor destroyed, rather converted from one form to the other. Yes, this is more of a physics concept. Yes, you might study this more in energy, but it also pertains to exactly what we're talking about here. Energy can be transferred through contact or without, and we call it something different, right? Radiation is the transfer of that energy across the space, could be like the vacuum of space, very important to the latter part of our semester here. So, transferred across space doesn't have to have direct contact, right? Just like if you were to walk up to an eye on your stove that's on and you can feel that from a distance, right? You know, no, 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 don't touch that. That's still hot. So you can feel it from a distance. That's radiation, the radiation of heat. Conduction, that's direct transfer. If you put your hands down on your desk and you leave it there for a few minutes, you can you can kind of give yourself an example of what conduction is. That energy is transferred from your body to the desk, that thermal energy. And if you take your hands away, then you can still feel where your hands were because you have transferred or conducted that heat from your body to the desk. The other example is if you like playing weird games like that, you could just reach out and touch that eye like Dr. G did when she was 3 years old. My mom sat me down on the counter and said, "Now, Katie, don't touch that. That's hot." Well, what did I do? Because I'm a button pusher. I had to touch that eye, and of course, I got burned really bad. So I learned conduction firsthand. It was hot, and I got burned. Convection again is another one we've talked about so much, right? The transfer of heat, energy through movement of liquid or gas. Again, your examples there would be convection in interior Earth, which is the movement of liquid, right? And then the convection of the atmosphere, which is the movement of that gas. Light, we have spoken about bits and pieces. One thing I love about having taught earth science for as long as I have is we can kind of give you a little bit of information here or there to make information later on down the road a lot easier to digest. And light's one that we've talked about. We talked about with waves, the electromagnetic spectrum. We kind of hit on that just a little bit, the visible light spectrum. The visible light spectrum is all of the light that the human eyeball can see, okay? It is all white light, incandescent light, fluorescent light, and obviously light from the sun. This is white light. And that light is actually broken into different frequencies. And those frequencies are Roy G. Biv. And I'm sure that sounds pretty familiar, right? The colors of the rainbow. Well, it's not just the colors of the rainbow. These are actually different frequencies, different wavelengths of light. Red being obviously has the longer wavelengths and the lower energy and the lower frequency, all the way up to violet, which has the highest energy of the visible light and the shortest wavelengths. And this is very intuitive if you can think about it like this way. We know what infrared is, right? Infra means below, like infrastructure. Infra means below, so infrared comes just below red. And you probably already figured out the other end of the spectrum. What do you think comes beyond violet? And you'd probably be right if you said, or you would be right if you said ultraviolet, right? That comes just beyond. So what we can see, what the human eye can detect, is right in that nanometer range of the frequency of red to the frequency of ultraviolet. Why is that important? Well, because everything that you can see outside during the daylight, of course, when the sun's out, right? That solar radiation, that solar light is made up of those waves that we just discussed. And I know you've experienced this. Have you ever worn black on a hot day, like, or even not even doesn't have to be a hot day, right? When you're outside, have you ever noticed the difference from wearing maybe all black to all white? I'm sure that you have, right? Because black absorbs radiation, right? It absorbs that heat, it brings it in and it holds it and it makes it hotter. Whereas white is going to reflect. Why is that important? Well, we're going to talk about solar radiation and what traps it more. Is it the crust being darker or is it the water that's being lighter? Like what's going to trap that more? So this is an important concept wearing that black shirt or that white shirt and how you feel standing out in the sun. What's absorbing more of that radiation? The sun does radiate energy at many wavelengths. I do want to reiterate that point. It's not just visible light that we're talking about here. There are many other wavelengths or energies that we're going to discuss in the electromagnetic spectrum that the sun does radiate as well. The energy from the sun does travel millions of miles, 93 million miles. That's where we are here in our little Goldilocks zone. Third planet, right, from the sun, 93 million miles. Think about that. And it takes about 8 seconds for that light to get to us. That's pretty incredible, right? 93 million miles, and it only takes about 8 seconds for that radiation to get to us, that light to get to us here on Earth. Again, more on that when we get to space. So what is solar radiation? It's all of these things. One more time, I want you to understand that it's more than just the what our eyeballs can detect out there. And you know that because on a hot day, you experience that heat, right? That's a little bit different than what our eyeballs can detect. So it also radiates visible light, ultraviolet radiation, right? We know that could be good. It could be bad. Infrared, remember that was just below red on that visible light spectrum. That's like your thermal cameras, what that picks up, right? And then we have radio waves, X-rays, gamma rays. When we get to talk about space, it's pretty cool how we use these things. So you think you just turn on a radio right in your car. Well, what is that? Those are waves. Well, what else gives off those things? And you wouldn't think that, but other stars give off these different types of waves, these radioactive waves as well. And we can pick up on those and kind of get a good visual of what's closely out there to us, right? Beyond what we can see with Hubble telescope and things like that. So also nebulas and other galaxies give off these last three right here: radio waves, X-rays, and gamma. Big mamma jamma. Those are bad gamma rays. Okay, think of the Hulk. What transferred him or made him into the Hulk, right, was gamma radiation. So these are all of the things that exist within solar radiation, not just that visible light. When we talk about this in class, I'm going to ask you this question, but do you think there are waves that the human eye cannot detect? And I hope at this point in our lesson you can say, for certainty, there are, both above the spectrum and below the spectrum of what the human eye can detect. All right, Earth. How does this affect us here on the Earth? Well, Earth's surface absorbs, going back to what I was talking about earlier, Earth's surface absorbs the sun's energy just like that black shirt that we were talking about, right? So land is darker. Land is going to absorb most of the radiation coming from the sun, the heat coming from the sun. Ice caps, that's going to reflect radiation. Also, water is going to reflect a good amount. It's also going to absorb some, but it's going to also reflect a good amount of that radiation. Overall, Earth absorbs about 50% of the solar energy that our atmosphere allows through. That's super important. If you studied atmosphere, if y'all watched those lectures, then you know not all of that radiation gets through our atmosphere, right? Have you ever seen, this is kind of an important question, so pause if you want to sit and ponder this for a second. Have you ever noticed, like on a hot day, wavy patterns coming off of hot asphalt or concrete, the darker asphalt, really? If you've noticed that, what you are witnessing is convection, right? The heating and the rising and the cooling and the falling of material that close to the surface, that surface is extremely hot because it's dark and it absorbs that radiation from the sun. And so what you're seeing when you see those little shimmeries, you're seeing that heat's being released from the asphalt and coming up into the air. Okay, so you're seeing the beginnings of convection there. So that ripple again is convection. That's the transfer of heat from the ground to the air. And this does happen on a global scale. So this happens, of course, that's why we're giving you this example. This happens on a global scale, right? Convection is transferred from the surface of the earth that absorbs it more, especially when we're talking about the land, right? And then it is released into the atmosphere and it distributes heat. I won't say heat energy evenly, but it does distribute energy around, heat energy around the globe through the atmosphere. It's obviously not equivalent, but it does help a little bit with distributing that heat energy around the globe. Earth's atmosphere does release, and this is going to be a key concept when we get closer to the end of this lecture today. Earth's atmosphere does release heat energy back into space as well, so it doesn't hold it all, right? What do you think would happen? That question was, we'll talk about that in class. What do you think would happen if it didn't release? What kind of planet would we be like? Can you think of a planet? What kind of planet would we be like if we did not release that solar radiation back into space? Again, I'm going to talk to you a lot in class about this, but think about a very hot planet. You think about the planets in order, and you'd be probably surprised to know that the closest planet to the sun is not the hottest planet. Okay, so what other planet would we be like if we didn't, if our atmosphere did not release that radiation back into space? This is just, I would love for you to play with this when you do this in your self-paced Nearpod, but this is just a visual of the surface of the sun. You can see all kinds of solar phenomena, which we're going to study in the next unit. You can see flares, and I don't see any prominences particularly, but no sunspots either. But anyway, I put this in here so you can just kind of peruse that a little bit. So pause it and take a look at that in the self-paced Nearpod. All objects emit radiation. This one throws kids for a loop, right? All objects emit radiation. Okay, and I want you to think about, if you ever seen those ghost hunter shows, they got that little camera that covers their eyes, right? And they're looking around and they're looking around, and all of a sudden they're like, ah, there's a figure or something standing there. I don't know. Or there's a hot spot. If you've ever watched any of those, you're probably familiar with that. But if you've probably seen here or there some kind of picture of thermal imaging, and you know that cold objects are going to appear to be blue, right? Bluish, greenish. And then as we move up that spectrum, as the objects get hotter, then they are obviously more orange, more red, um, and then white. This is important though, because if all objects didn't emit some form of radiation, then we wouldn't be able to see the objects on the camera to begin with, not even the cold ones, right? So this is a key concept here. Make sure you understand objects, even though some of them are cold, but they don't emit their own heat, um, they are still emitting some form of that radiation. And a couple images here of the sun, I thought were pretty cool. All right, here you have an example. Radiation, like all waves, it can be absorbed, transmitted. We talked about the behaviors of waves here recently, right? We said all waves behave in 4 certain ways: reflection, refraction, transmission. Absorption, scatter is also it's under that category of transmission and how it is being transmitted. So radiation, like all other waves, can be those things too. It can be absorbed, it can be transmitted, reflected. It can also be reflected, right? We're talking about Earth's atmosphere does that all the time. It reflects solar radiation. But I want you to take a look at these 2 bulbs here. You've got the one on the left, a more incandescent light, right? The one on the right, that bulb is very transparent. And what would be, pause it and think about this, what would be the difference of transmission of that light, that white light, through those bulbs? And in a face-to-face class, what I would do is I would ask my kids, are you seeing all of it or are you seeing part of it? Is it like frosted glass in a bathroom window, um, or a shower curtain so that some light can get through, but not all? Or is it perfectly transparent, right? So ask yourself, Norton, how do you think that the light would behave differently given the outside of these 2 light bulbs? All right, solar radiation is absorbed, right? Absorbed by many things: sand, grassy fields, forests. Water does absorb, it also reflects a lot. The ozone layer in the stratosphere, you learned this past week, right? The ozone layer absorbs radiation. Clouds absorb and reflect radiation. So there's a lot that goes into this process of balancing energy. Re-radiation is another word. Sometimes you won't see re-radiation. Sometimes you'll just see the word radiation. But either way, tomato, tomato is kind of one of those things. Some scientists use it, some won't. Earth's surface does re-radiate. What does that mean? So it gives that back. And without going into way more detail that's a little bit above our pay grade, like that's going to come in at an intense frequency, a higher energy. The solar radiation is going to come back in. But due to greenhouse gases like carbon dioxide, it is released in longer wavelengths and less energy back out into space. And so radiation does occur. The Earth itself, the geosphere, does give that radiation back out to space due to those greenhouse gases like carbon dioxide. The atmosphere re-radiates approximately 60% of incoming absorbed solar radiation. And those numbers will make sense in just a second. Earth's surface re-radiates approximately 10%. All right. Let's get to the numbers because that's going to help you. Oh, that is too small. I don't like that. We call this Earth's energy budget. All right. So the Earth has to budget, has to maintain what it's receiving and what it's giving off, right? If it receives too much, what happens? Right? If it gives off too much, what happens? So interestingly enough, and Earth, y'all, you guys know I talk about this all the time, is just an incredible just phenomenon how this actually works. It's insane, right? Earth actually maintains a relatively constant average surface temperature, okay, by re-radiating and reflecting as much solar energy as it absorbs. Does that change over time? So for those of you that are screaming at me right now about climate change, does it change over time? It can. Can human beings speed it up? We can. If we get rid of too much, or if something happens in our existence to get rid of too much, could that cause issues? Yes. If I don't know, if there was great tectonic shifts and volcanic activity increased and carbon dioxide increased, and we started holding, or Earth started holding in more, could that change? Yes, it all could. Absolutely. Right. We've seen and we've talked about with the GTS, and we've talked about with early Earth's atmosphere how those changes have happened. But on a large scale, really, Earth maintains a relatively consistent average surface temperature, again, by giving back what it takes in. All right, so to look at the numbers, and this would be one I would screenshot. I always tell you, screenshot, screenshot. This would be one I would screenshot, Unit 4 folder. Incoming solar energy, now 100% of what comes in. 30% of that is reflected and 70% is absorbed. Okay. I also corrected some of these things in here, and it looks like maybe I went back to the last one. So sorry about that. You'll get the corrected one in class. Incoming solar energy, 100%. So 30% is reflected, 70% is absorbed. And we saw that on the last slide, right? Of that 70%, we had 10% here and 60% here. Eventually, that 70% is re-radiated back into space from those greenhouse gases like carbon dioxide, releasing it from the geosphere. And we also have here the final numbers. Total solar radiation coming in is 100%. Total solar radiation going out is 100%. Okay, so we have what we're taking in, we are also giving back, and that's what allows us to budget energy, solar energy here on Earth. In terms specifically to that, re-radiating and reflecting, you need to know those words as being a way of giving back, and then absorption as a way of taking in what we need. Okay, this keeps Earth's temperature balanced. And again, what do you think would happen? What do you think? And this is a question I want you to bring. I gave you a little bit of a hint towards that, but bring this question to class. Have some answers for me. Let's discuss when I see you again. What do you think would happen if this became out of balance? What would happen if Earth didn't budget energy as efficiently as it is right now? There are some great questions in the time to climb. Okay. I'm going to be, for my students, I'm going to be particularly looking at this when I go through your notes. So make sure you take your time and answer those appropriately. All right, guys, all I have for you today. See you next time.